Okay, so I'm going to be talking about the dynamics of galaxies in the local group. So within about 3 megaparsec or so. So what this diagram shows is like a simulated velocity field. And these black dots show like the positions of real galaxies. And this is Milky Way and Andromeda separation to scale. So we'll just get going with the equations governing this system. So first of all, you have to remember in a homogeneous universe, if you have two test particles with some kind of separation vector r between them, then the length of it just scales with the scale factor of the universe. So it's just like a homogeneous expansion. Therefore, you're going to get this equation for, the equation of motion, right? So if you add in gravity from the Milky Way and Andromeda, you add in, of course, these two terms. You can derive this from general relativity if you like, but it's you can think of it in Newtonian terms as well, as extra forces. So to make this model work, we're going to have to make some simplifying assumptions. Some of them are more accurate than others. So first of all, we assume that early on, all objects are following a Hubble flow, so uniformly expanding universe, no peculiar or inhomogeneous sort of motions. And therefore, it's strictly symmetric initially. At later times, we're going to assume the mass in the local group is dominated by the Milky Way and Andromeda. They're known to be on an almost radial orbit, which means that the local group is essentially axisymmetric. Right? Both the initial conditions and the governing equations are axisymmetric. So what we do then is first of all, we solve the Milky Way Andromeda trajectory, and then we start test particles out in like a wide region. We don't allow them to start too close to the Milky Way or Andromeda, basically because they can't have formed from nothing. They must have formed from material within a certain region, which they sort of accreted early on. So we exclude test particles starting very close to them. Now, to handle particles approaching either galaxy closely, we basically had them accrete, and that did actually raise the mass of the accreting galaxy, which is included in a model. So the forces, though, are not, you can't just extrapolate them to very short distances. The reason is that these galaxies have flat rotation curves, so we know the force must be inverse r close to the galaxies. But obviously, if Newtonian gravity is right, it's inverse r squared as you get further away. Then naturally, our model will have certain deficiencies. First of all, interactions between galaxies in the local group, other than the Milky Way and Andromeda, these aren't included, right? They're quite light, low mass, so they would have caused like a velocity dispersion of about that order. If you look at the internal velocity dispersion, there's a maximum possible from like a close encounter between them, sort of thing. We did include the galaxies like the Triangulum. We do include the Large Magellanic Cloud, which I'll come to it later on. Tides from galaxies outside the local group, things like Centaurus A. Well, Centaurus A we actually include directly, but more distant things naturally, we can't include everything. Regions too close to some of those objects we simply didn't analyze because our model might not be accurate. So I've already mentioned how we transition the force from r inverse to r to the minus 2, but the exact recipe is somewhat arbitrary. So the first step here is to solve the Milky Way Andromeda trajectory. So you start with some variable like initial separation. You vary it until you match the right final separation of 783 kiloparsec. So the error margin on that is about 1 part in 30. And that is the first step, obviously, because this tells you the gravitational field in the local group. What happens next, you start test particles out somewhere around here, they shoot outwards, and then you get something looking like this at the end, with the tracer particles, tracer galaxies, which really are there. So if I zoom in on this region, you'll see that close to the local group, things should be coming inwards because of the gravity from the Milky Way and Andromeda pulling them in. and further out, of course, they should be receding. It should be like a zero velocity surface somewhere around here. But it's not like a spherical thing. So obviously this problem is in spherical spectrum. So if you look at a Hubble diagram, which is where you plot the radial velocity directly away from the center of mass of the local group, then you get points like that. So basically it converges onto this, the blue line, which is what happens in a perfectly homogeneous universe. It converges onto that at long range, but at short range, the velocities are lower because of gravity from the Milky Way and Andromeda, which we see around here. Yeah. So that's the basic idea you want to take away. That gravity is reducing velocities because it's attractive. So the data we're using is coming from this catalog by McNasty from 2012. The targets, so it has a lot more than 32 galaxies, I should say. So the targets we select are basically the same as Anaerobia from 2014. They do like a similar analysis, and they decided on these targets. We excluded Andromeda 18 because it's in this disturbed region around Andromeda where you can't predict velocities properly. And these two galaxies are binary, so they can't be counted as separate objects. You use the center of mass, right? Yeah, the velocity field, it has to be smooth near the target galaxies. If it's not smooth near them, so it's crossing trajectories, then you can't be sure if a galaxy is at a particular position, like what velocity it should have. You might be able to measure its actual velocity very accurately, but you can't be sure what it should be, so that's not good. So we reject the targets like that, but that's rare because Anaerobia is probably done much slower for us. Satellite galaxies obviously not in our analysis because they're going to be in a disturbed region around the Milky Way or Andromeda. So that we look at distant sort of non-satellite galaxies, field galaxies almost. So the analysis we do is Newton-Raphson two-dimensional stage to get test particle trajectories landing exactly where an actual galaxy is. That's the main thing in our algorithm, which is the key thing. Once you have a test particle landing where actual galaxies, you can say how much should velocity be in this model. And then you project that onto the line of sight because we only really have the radial velocities. In the future, we might have proper versions, but for now, we get the galactocentric radial velocity. There's some other corrections for the motion of the sun in the Milky Way and so on to get like the heliocentric one. But the other important thing we have to do is like obviously errors have to be handled. The way we do that, first of all, to handle the distance uncertainty, you increase the distance from the Milky Way by like the uncertainty in the distance. You repeat the analysis. Actually, you can reduce it instead, and that doesn't do anything. It's the same answer. We also have to add on, this one's quite simple to handle, is there actually is a real error on radial velocity measurements as well. So that's simple enough to handle. Then we also add in a special like extra variance, which is, well, physically it would correspond to interactions between local group dwarf galaxies and other things as well, like large-scale structures, for example. Basically, it's designed to, we put in as much as we need in order to make the model and the observations fit. And if you find very large values, that the model does not work very well. So one thing I'll do is explain how much is a reasonable value later on. But whatever the value is for field, like dwarf galaxies, you expect a much lower value for Andromeda because it, if like dwarf galaxy hit it, it wouldn't change its velocity very much because of its high mass. Also because of its very low distance from the Milky Way compared to other objects. It's not so strongly affected by tides from more distant objects. So it's the probability is a lower value for Andromeda. But that's not actually crucial for our analysis. So what we do after getting a Milky Way Andromeda trajectory and doing all that, we get 32 maps looking like this, which tell us as a function of the local group mass and the fraction of this mass in the Milky Way, or the mass of either galaxy, if you like, what the radial velocity of the galaxy should be. Now, you can see that Andromeda basically is sensitive to the total local group mass, but it's not really affected by the fraction of this mass in the Milky Way. So you might expect that because the forces between the Milky Way and Andromeda are not really sensitive to how that mass is distributed. Whereas if you look at sextans A, then you see that that would actually give a very strong constraint on the Milky Way Andromeda mass ratio. The reason being that it's somewhere else and the local group's not spherically symmetric. The exact way in which the angular dependence manifests itself will depend strongly on the mass ratio, and it will have a big impact on the radial velocity here. So you can see that even with 2 galaxies, you could get reasonably strong constraints on the parameters. But actually we have 32, so you should be getting a good idea of like what the parameters are eventually. So I'll just show you like what happens if I plot the best fitting model. The model radial velocity is here and the observations are up here. The basic idea is to add a scatter about the model line. So the blue line is the line of equality, and find out how much extra dispersion you need to add to make it work, basically, to reduce the chi-square to order 32. So.
But there's a bias there.
Yeah, I'll come on to that.
Okay.
So if you just do the calculations there, you find it takes about 55 or so kilometers a second. If you treat Andromeda just like other galaxies, then it might be 45. So it's somewhere around that. Yeah. If what we did then was to try and answer your point about why galaxies seem to be systematically above like the model prediction line. So one obvious possibility is that we've sort of used a very high like local group mass or something, even though we have actually used whichever model fits best. What you see then, if we remove the effect of gravity altogether and just found out what happens in a homogeneous universe, then you get like a model prediction. So this is a very bad model, but it's a model, and the observed radial velocity up here. So again, the line of equality, but you see some galaxies which are above it. So some galaxies are flying away even faster than if there wasn't gravity from the Milky Way and Andromeda. So this is slightly weird. We'll come later on to why that might be. First of all, like what might be a reasonable value for this extra dispersion? So first of all, if you see a value of 45 kilometers per second, in 3D this basically corresponds to 1.7 times as much. This is about 18. That's quite high because local group dwarfs are rotating at like about 15 kilometers a second. So, and large scale structure again is not having such a big impact. So velocity is also being more often above the model than below is slightly weird. So it's not like a random dispersion really, it's like a biased one way. And therefore we decided the interactions between dwarfs in the local group are having some difficulty explaining the observations. So we also look carefully at other explanations like tides, Milky Way Andromeda satellites, which I have a bit of section on that at the end. And we came to the conclusion lambda-CDM does not match the observations of the positions and velocities of the local group galaxies. So we considered modified Newtonian dynamics and see what that has to say about it. We haven't tried this directly, but it does still have certain consequences which we're reasonably sure of. So in lambda-CDM, the Milky Way Andromeda trajectory is just like this. You could raise the mass, but you can't really get a fast flyby. The reason is when the galaxies get very close, because of their dark matter halos, they would just merge. So this is basically what has to happen in lambda-CDM. You can't really invent like something, a flyby there. However, in modified Newtonian dynamics, a flyby is inevitable in somewhere around this kind of time frame. Because Andromeda is on an almost radial orbit with respect to the Milky Way, it's quite a close flyby. And actually you can't avoid a flyby like that in this model. So it's quite different, and that will have consequences. So the way in which this might help address the observations is via what are called gravitational slingshots. So if you have a heavy galaxy like the Milky Way moving at 5 kilometers a second and a dwarf moving this way at 1 kilometer a second, then this is equivalent to the Milky Way being still and the dwarf approaching at 4 kilometers a second. So that's the Galilean transformation. Now, what can happen to this galaxy is it can go on an orbit like that around the Milky Way. The Milky Way might reverse the velocity of the object, in which case the object is now moving at 9 kilometers per second instead of 1. So basically it can gain a lot of the amount of speed it can gain is basically limited to twice the velocity of the Milky Way. Probably it will be like about 1 times, but that's the basic idea. So if you then try and see a histogram of the of the observed minus the model predicted radial velocity, so the radial velocity discrepancy, then you'll see something interesting. So in blue, what I show are the galaxies which have radial velocities below the model predictions. So these are distributed in like that, see. Now, if you try and overplot a 15 km per second Gaussian on top of that, you can see that's worked fairly well, right? So I mean, you don't expect these things to match exactly, but that shows that basically these objects more or less consistent with lambda CDM. There's nothing wrong with 15 km per second discrepancy. However, the objects with radial velocities above the model predictions, they're shown in red, have like some really unusual feature and can't possibly be described by a 15 km per second Gaussian. So what I think has been going on is that there's objects which never interacted with the Milky Way or Andromeda, which are following a population here. There's another population here flung out by the Milky Way, and a smallish population here flung out by Andromeda, which is heavier than the Milky Way. That's my understanding of these results. Just to recap, in MOND, you have a fast close flyby between the Milky Way and Andromeda, which causes dynamical heating of the local group. Well, that means that it raises the velocity dispersions by flinging some galaxies out at very high speed, which is something that also occurs in lambda CDM, right? But in lambda CDM, the Milky Way and Andromeda have never been moving very fast because they've never approached each other very closely. So the process does occur, but it's much less efficient. So that will become clear on the next slide. If I show the Hubble diagram, so radial velocity from the local group center of mass against distance from there, these just the distances of the observed galaxies, just to give you an idea. So what you can see is that although this process of slingshotting has created like a disturbance to the velocity field in this region here, that doesn't actually affect any of the observations because it's just stopped at 1 megaparsec or so. However, if you use MOND, then what will happen, because you can fling galaxies out much faster, basically the whole local group has like a disturbed velocity field in this model, essentially. So you can see that some of these galaxies, for example, they could be on this line, material that never interacted with the Milky Way or Andromeda and have a fairly low radial velocity. But they could also be up here with a very high radial velocity. These galaxies are following like something like a Hubble flow line. This is the usual Hubble line corresponding to 70 kilometers per second per megaparsec. This one has a higher gradient. The reason for that is that basically those galaxies were flung out by the Milky Way or Andromeda. But to be flung out that fast, it must have happened close to when the flyby took place, so that they were moving very fast. And therefore, they must all have been more or less in the same place at the same time. So what you see is basically that distance is velocity multiplied by time. And therefore, things which are further away, because they've still had the same amount of time since the flyby to get there, they just have to be going faster. That's the basic idea behind the simulations. What must have been happening there. You can, one thing to bear in mind is that that doesn't apply to all the objects, right? Some objects might not have been flung out by the Milky Way or Andromeda, and they should be more or less consistent with lambda CDM. So that will apply to some objects. Actually, it's probably quite rare for a galaxy to pass very close to the Milky Way or Andromeda at exactly the time they're closely approaching each other. So that might not happen for too many objects. But it should happen for some objects, and they'll be following this relation that the excess radial velocity is more or less proportional to distance. And therefore, what we're looking for really is a signal towards the outskirts of the local group, where the excess radial velocity becomes, well, that maximizes the difference between the two models. So what I'm going to show the next slide is the delta GRV's plot against distance. Remember, at long range from the local group, the model prediction is basically a pure Hubble flow, more or less, right? Because gravity is not so important. So pure Hubble flow looks like this. So if you divide distance by time for these objects, you recover an age of about 14 billion years. So now the data looks sort of like this. So you see that a lot of objects do have delta GRV of about 0, right? I mean, there's going to be some scatter, but yeah, it's like a band here which is more or less 0. However, there's also another band here, which I think actually is more or less proportional to distance outwards. If you try and work out like the excess radial velocity, it's like 100 kilometers a second at 2.5 megapascals. So it's a 40 kilometers a second excess for each megapascal. And if you just add that on to the usual Hubble law, you get a higher effective Hubble constant. That tells you that you're seeing basically the remains of an explosion 9 billion years ago. So obviously not the Big Bang, but something like 5 billion years later. Right? That's what I think is going on. Now, if you try and actually calculate the Milky Way and Andromeda trajectory inborn, then you would get something looking like this, which is to say a flyby somewhere around here. Actually, this is a high estimate for when the flyby was. It will probably be in that range. So, if you try and show what I showed from the last slide, you try and divide distance by velocity and roughly estimate when the flyby should have been to explain the distance-velocity relation. You get something sort of in that range. So we're going to do that work more accurately, right? It's a rough idea. I'll explain in the next slide, but the Milky Way has a thick disk, which we think formed somewhere around there. And all three age estimates seem to agree. So I'll come to the thick disk now.
John, how are you getting these different estimates? What's
yeah, I was going to explain like why we got the thick disk from. So there you go. Now, what I was going to say is that the thick disk of the Milky Way, which is which means that the Milky Way has a thin disk and it's being dynamically heated. So what the graph you want to look at is the bottommost one, the vertical velocity dispersion in the Milky Way's disk, as a function of look-back time. So this is 3 billion years ago, and this is 10 billion years ago. And if you draw a line here, you can see that there's been a sudden sharp rise in the velocity dispersion for stars older than about 9 billion years, which is kind of thing you might expect with a minor merger or the flyby of another heavy galaxy. Now, for my master's project, I was finding out that this heating event was stronger in the outer parts of the galaxy, of our galaxy, which is characteristic of tides. But anyway, like you can look at what these authors say. So this is based on Hipparcos data, I should say, to get accurate like distances. So what they say is that they see a sharp increase in the velocity dispersion at 9 plus minus 1 giga-year, and it's consistent with models in forming during a minor merger. So obviously in Lambda-CDM you don't really get like a flyby of another heavy galaxy, but nonetheless it's giving you an idea that something seems to happen to the Milky Way at around that time, which is the kind of thing that would happen with a flyby of Andromeda. Now another thing that I wanted to show you was if we simply look at these very high radial velocity objects towards the outskirts of the local group, then you can see that they, by rotating in 3D, you can see that you can get them to lie close to a plane. That's important because if the Milky Way and Andromeda did actually fling them out very quickly, then they could only do so more or less parallel to their velocity at that time. Now, we don't know which direction the velocity was, but one thing is for sure is that so the Milky Way and Andromeda would have been going within a certain plane, their common orbital plane. And therefore, these high velocity objects should mostly lie close to a plane. So it's kind of interesting that that actually does seem to happen. And that also the plane includes the Milky Way and Andromeda. Obviously, if it didn't, then the theory makes no sense. But to quantify the significance, what we do is we randomize directions towards the 5 of the galaxy I was showing on the last slide, the most discrepant ones. Not Andromeda though, just the local group like field galaxies. We select 4 out of 5 of them because one obviously didn't fit the pattern so well. And we find the best fitting plane, and then there's 5 combinations, so you get 5 answers. We take the lowest one, and you plot out the histogram, right? So that looks like the histogram here. The observed value is the black line. So you can see it's actually not very likely you get a thinner plane than what we saw, even though we've only got like 5 objects, and we're allowing for not choosing all of them. So that's one thing. But one more very important thing is what orientation should this plane actually have? So to find out, I did certain calculations in March, which are quite simple, which are based on assuming that the Milky Way and Andromeda, they exert sort of tidal torques on each other only at the exact moment when they approach closest to each other, and only on the side of each galaxy which is nearest the perturber. So the Milky Way is here, Andromeda is over there, only the Milky Way on this side gets a tidal torque. It's a rough approximation, but it tells you more or less which way you expect the material to be tidally torqued, which way you expect it to gain angular momentum. Now, what the trick is to try and change the parameters to get the material in the Milky Way to gain angular momentum in the direction of its disk of satellites. So the Milky Way, for those of you who don't know, has a plane of satellites sort of oriented at 90 degrees to the disk. And Andromeda has a similar plane of satellites where it's only at 50 degrees to its disk. So you try and basically produce those disks in this flyby. You also need to know that with a 1/r force law, the line between the objects is rotating about 180 degrees, since the time of closest approach. So what you can do then, so first of all, if the black line is like the Milky Way Andromeda line now, and the orbital pole of the system, so the orbital plane is in blue and the orbital pole is the red arrow for rotation around that. But how do we know that? Well, we don't know that for sure, right? The orbital pole could just as easily be in that direction instead. As long as it's orthogonal to the Milky Way Andromeda line, it's a valid orbital pole. So what we do is we try various angles, sort of going round like that, and see which ones work best. Yeah. This is the orbital pole position as you go south along the arc from a particular point, which satisfies this constraint of being orthogonal to Andromeda's sky direction. And there is some uncertainty on the rotation angle since the flyby. And this shows you how good a fit you're obtaining to the planes of satellites of the Milky Way and Andromeda. So a lower chi-square is better, which means that these blue regions are what you want to see. What this is showing is that the orbital pole has to be within this range of angles basically for it to work. So we're not able to obtain a good constraint on what the rotation angle since the flyby was. We already knew that more or less. The main thing is we get a good constraint this way. But just to say there's no viable solutions over there. So these wouldn't really work. So yeah, the important thing now is to look at the sky directions of all the planes we've just been discussing. So this is a galactic latitude and longitude plot, just showing sky directions. So some of the basics, the Milky Way Andromeda orbital pole, you can actually measure directly by looking at which way Andromeda is moving in the sky, the proper motion. And that gives you an answer here, but the uncertainty is reasonably large. And there's some more recent controversy over whether that's actually correct. The Milky Way, the direction of its disk, the angular momentum of its thin disk is over here by definition. For Andromeda, it's over there. The important thing for the Milky Way, its system of satellites, it has an orbital pole here. So basically, the satellites are in a plane like this, and this is the orbital pole direction. For Andromeda, it's over here. What I was showing on the last slide is that actually we need the Milky Way Andromeda orbital pole not to be at this point, but at this point, which is consistent with observations here, but that's where I'd like it to be. The main thing though is that the distant high radial velocity objects, I was showing a nice line through them, so in edge on view. That means you can find a sort of nice plane which fits them. The normal to that plane is over here. So that's kind of matched closely with where we need it to be. Now just a word of caution, like it might actually be pointing the other way because we don't have proper motion, so we don't know if it's actually rotating in the right sense. But still, like this is reasonably impressive. I think so. Is this all a coincidence? What's the probability associated with this being a coincidence? So to do that, answer that question, we randomize the directions to the galaxies, except Andromeda. But you select 4 out of 5 objects with the highest radial velocity, use the thinnest plane. So like before, but we added extra condition. First of all, you try and get the thickness to be below the observed value. But you also want the plane normal to point within the red region, which is on the next slide. So basically, I'm saying that as well as finding a thin plane, you want the normal to that plane to be within this red region, just to get like a reasonably good alignment with both satellite planes. If you try and align it more closely with that, which might be more physically meaningful, then you might get a much smaller probability. So I didn't do that because I'm trying to be conservative. Anyway, if you do that, then you get a probability of 1 part in 3,500 or so. That's with only 6 objects, including the Milky Way and Andromeda, by the way. So there's only 4 external galaxies like that. And that's reasonably significant. It might be like a 3 sigma event or something. Now, another interesting thing you can do is try and project all the galaxies into the plane we found, that is defined by the distant high radial velocity objects. The Milky Way is here, Andromeda is here. We think it's rotating around in this sense. And the sizes of the symbols and the colors tell you how much the radial velocity is discrepant from the best fitting model. So these galaxies are flying upwards really fast. These ones also, this one not very much. If you try and compare that with the simulation, you notice some interesting similarities. So for example, there's this load of galaxies in the simulation which are flying outwards really fast, which sort of corresponds to these objects. There's some objects here which corresponds to that. And on this side, there's not much there. Similarly, on this side, you don't see anything flying away really fast. So it's kind of interesting. Now, that just shows you the same thing again, if you wanted to see it. So just ignore the black dots. The simulation is the main thing. So one thing we've been asked about recently is to include the Large Magellanic Cloud in our analysis. This is a heavy, it's the brightest Milky Way satellite galaxy, which is visible from the southern hemisphere. It has a very high motion relative to the Milky Way. But it's very nearby, so basically its mass just, you can assume it just adds on to the Milky Way. So why are we really worrying about it? Especially considering it's too light to affect things directly, because its rotation curve is not much higher than 90 kilometers per second at most. So the reason is that it can affect the analysis indirectly, because although it can't do very much dynamically, what it can do is it can shift the center of mass velocity of the Milky Way system, which is the Milky Way plus the Large Magellanic Cloud, basically. One way to think about what's going on here is to say that our equations have to have a correction for the sun not being static with respect to the Milky Way center. Similarly, now we have to change that slightly to saying the sun has having slightly different velocity with respect to the Milky Way system, these two, than with respect to the disk only. So you can make a small adjustment to your equations to allow for this. The main thing that actually happens though is that you just add a constant vector to the predicted velocities of all the galaxies in the local group. The vector is parallel to the direction in which the LMC is moving with respect to us, but nonetheless that's the basic idea. So what we did is found out how much this extra dispersion we need, basically the mismatch between lambda CDM and the observations. We tried to find out how that varies if you change the Large Magellanic Cloud mass. So if it's 0, then you get 45, 46 kilometers per second. But if you increase LMC mass, it drops a bit. So people were thinking this might be how to explain the observations. but actually it's not, because of course if you add too much, you overcorrect. I mean, you can't just say, these are the model predictions and we're going to add a really large vector this way and it's going to match the observation. Eventually you're going to make things worse. That happens round about here, so this is still not a very good match. So just a few other things we've managed to extract very recently is the total local group mass, which people are reasonably sure is above 2 trillion solar masses. So again, you can see, although it keeps dropping, you don't want a too heavy large magnetic cloud. And the Milky Way mass, just to show that we had to impose a restriction on the large magnetic cloud mass to stop it being like unphysical, and that hasn't had too much of an effect. So the fraction of the Milky Way is like this. We think it's less than 0.5 because Andromeda is larger and spinning faster. So we don't want LMC masses that beyond AV. And the local standard of rest is the circular velocity in the Milky Way disk at the sun's position, which independently is constrained like here. We found, we allowed it to vary a little bit, but there's no tension with that measurement. So there's no tension with these measurements. No good reason to change that, like at all, in fact. So my conclusions from this investigation is that mainly lambda CDM does not describe local group galaxy positions and velocities very well. So we tried a wide range of models, and the main thing that's going wrong with the model is that we see a lot of distant galaxies with very high radial velocities. So somehow they've been flung out at a high speed, and at about the same time as the thick disk of the Milky Way formed. So these things are model independent statements, more or less. If you also use MOND, then you'll see that there's a third coincidence, which is that Milky Way and Andromeda flyby in MOND would have been at about that time as well. These galaxies, about 6 of them, lying close to a plane, which, if they were actually flung out by the Milky Way or Andromeda, like the only 2 galaxies heavy enough to plausibly do that, then that plane would have to be the Milky Way Andromeda orbital plane, right? If you've understood things right. If that is so, then the orientation of this plane is about right for creating the satellite galaxy planes around the Milky Way and Andromeda. I haven't talked too much about, but they exist, and the orbital plane here would have been about right for creating both satellite planes. So you need more detailed models to test that, but roughly that seems to be so. Of course, like an actual Milky Way Andromeda flyby is only going to make sense in modified theories of gravity, where galaxies don't have dark matter halos that would cause automatic emerging whenever they get very close. So that's my conclusions. Thank you all for listening. Any questions?
Any questions?
I was just wondering if you considered the scenario where the Milky Way did have a major merger at roughly the time of the age of the thick disk, and whether that could reconcile, that could throw out these objects as well. As
you have to worry about whether it would have, how much damage it would have done to the Milky Way's disk. I mean, even a fairly minor merger would have been enough to inflate the velocity, especially the much observed. A major merger might have done much more damage. So there's you have to remember, like, if a galaxy flies fast, to do even a little bit of damage, it would have to be quite heavy. But if it's merging, then it could be quite light and still do a lot.
But would it be able to toss out a few objects that...
Yeah, it would also be able to toss out some objects, like as it's moving very quickly. So it's possible. It depends on the velocity. So for example, if it's got like 100 kilometers per second, like flatline rotation curve, maybe, it can't fling things out much faster than that. And because of Hubble drag, that gets reduced a factor of 3 or so. So it'd be hard to explain why. I mean, it'd be hard to explain much more than 30 kilometers per second effect like that. Maybe that might be one possibility.
But then, just wondering, would there be any way to differentiate between different modified gravity theories with this sort of work?
Possibly. I mean, what you have to do is try and find out, like, so these things are very sensitive to the Milky Way Andromeda trajectory. What you have to do is find out in your preferred modified gravity theory, like, what does that do?
Okay.
If you know that, then you have a good idea of like what the rest of the local group should be doing and whether it's consistent with observations. Yeah.
At the beginning you said that we're assuming that the orbit between M31 and Milky Way is a radial orbit.
Yeah.
But I don't understand where the observations are coming from to tell you that. We've only got radial velocity measurements for about 100 years. We have no proper motion measurements.
Yeah.
So how do you know it's radial? Isn't that an assumption?
Slightly. So there is a Hubble Space Telescope proper motion measurement, like a 7-year baseline by Son et al. From 2012, which is what we were using. That constrains the the tangential velocity to be below 34 kilometers per second. So their measurement is 17 plus minus 17.
Okay.
I have one question.
Yeah.
Are there some straightforward, easy observations that you can do to distinguish between one scenario and the other?
I'm trying to think of some.
Between flyby and non-flyby?
Sorry, between.
So is there something easily that you can observe so that it tells you, yes, there was a flyby or no, there was no flyby?
Well, I'm trying to think of things like that.
Oh.
Yeah.
Are there any more questions? Oh, Paul?
I was both curious, why does MOND require this flyby between Andromeda and the Milky Way, and do all versions of MOND require this?
So there's very little difference between different versions of MOND, as I was showing in a recent paper about the external field effect. Why do they require flyby? It's because if you try and integrate the Milky Way Andromeda trajectory back in time, you've got a much stronger force between the galaxies. That arises because the force is declining as 1 by r rather than 1 by r squared. And because of the much stronger force, as you're integrating it back, they will fall into each other very quickly. And so you're always going to get 2 orbits basically. But if you also subsequently measure a very low tangential motion, then that implies a fast close flyby. It's fundamental concepts of the theory. Yeah?
So you're saying that because these galaxies are in this plane, that isn't seen in lambda CDM, it has to be MOND, right?
That was part of the argument. Even the fact of the magnitude of the radial velocity is already problematic.
Right. So if you compare this to simulations, these kind of velocities and planar positions of satellites don't occur.
So planar positions of satellites are very rare in simulations.
But there was a paper, I think earlier, late last year, that looked at lambda CDM simulations, and they find that 10% of galaxies have these kind of planar
I think there were some
structures.
issues with that. I think it ignored distance information, or you looked at sky positions or something. Also, one thing we did look at, my work wasn't primarily about the satellites, it was about more distant objects. One thing we looked at was in a lambda CDM simulation, how if you try to look at velocities of objects, radial velocities, and try and see how much dispersion there is about a Hubble flow line, then you get about 30 kilometers per second. So that shows that you don't expect much more than, because we've done a more careful modeling than just a spherically symmetric model, we expect that our model has maybe 20 kilometers per second discrepancies with what would actually happen in lambda CDM. Yeah. So that's a modeling accuracy I think we've achieved, and the referee is happy with that.
Last question.
Have you done the modelling in MOND? How does the interpolation function choice of that affect the results?
No, the interpolation function won't affect these results because these are in the deep MOND limit.
Oh, it's on deep MOND. Okay.
Yeah, because the Milky Way Andromeda, the mutual acceleration is about 1/60th of A naught.
Okay, so let's thank Daniel again for this.
There's some reasons for that. We came up with three factors that might be responsible. One is the cosmological term, which is the A double dot by A. That's one thing. The other thing is a reduced mass, because you think some mass is lost as the galaxies move up. And the other thing is tides, because if you look at the orientation, you see the Milky Way and Andromeda are like this. And now you have Centaurus A, which is trying to pull them apart. But before the flyby, they were very small.